Hi everyone and welcome back to NTE. In today's video we have a Euclidean geometry question. Right, so this is a student question and I'm not entirely sure about the source of this question. Right, but anyway, we'll let that slide for now. We'll just focus on the question itself. Okay. Right, so what is your strategy when it comes to Euclidean geometry? Well, first of all, you need to know your theory, right? And by know your theory, I mean more know how to apply your theory, okay? So know how to identify things on different diagrams, okay? Right, so that is literally the only best approach for Euclidean geometry, right? Be able to apply your theory to different diagrams, right? So that basically involves practice, okay? Right, and then also just understand that Euclidean geometry is a if-then, right, subject, right? So if this is the case, right, or if something is given, then something else happens, right? So if you can sort of like think of that if-then type of relationship, right, then you get to solving Euclidean geometry questions a little bit faster and easier, okay? All right. So with this one, this is question number 9 apparently. It says in the diagram below, A, B, C, and D, right, are points on a circle with center O. Okay, so as you're reading this, stop, right, at certain places before you carry on, right? So one strategy would be to read the whole sentence, right, the given information once, right, and then read it again, right, but then the second time you'll be stopping at certain intervals and you actually now start questioning the given information, right? So you're applying that whole concept of if, then, okay? Right, so for me, I like to read and then stop. I don't really read the whole thing throughout one time, okay? So if I do this again, right, it says in the diagram below, A, B, C, and D are points on a circle, right, with center O, right? So for that first sentence, okay, I can see that, all right, they're just establishing that these points A, B, C, and D, right, are on the circumference of the circle, okay? The next thing that they're establishing is that the center, right, is called O, right? So then I go to my diagram and I try to identify where that is, right? And I see, okay, there is the center O over there, right? Now there's a line going through the center O, right? So here's this if-then condition, right? So we know from theory, this is now applying the theory, that when we have this line, right, which we basically technically call a chord, right, that is going through the center and connecting two of the points on the circumference, right, then we call this line the diameter. Okay, so there you go. You're now starting to apply the theory. Okay, so that's what that first statement gave you, right? So now we're going to carry on reading, right? It then says that OB intersects AC at M, right? So we stop there. Okay, now let's analyze that given information, right? OB, right? Where is OB first of all? Okay, so there is OB, right? We see that OB is going from the center to the circumference, so we can say that OB is a radius, first of all, right? And then secondly, they say that it intersects, right? In other words, it cuts, okay? AC, right? So there is AC, okay? And they're just telling us that that happens at this point over here, point M, okay? Cool. Next, they then say the midpoint of chord AC, right? So if we had to read this again, it says OB intersects AC at M, the midpoint of chord AC, right? So M is the midpoint of this chord AC. Okay, so now if M is the midpoint of this chord, right, then we know that the midpoint basically divides the chord into two equal halves, right? So we now immediately know that the length AM, right, is equal to the length MC, right? So that is the if-then relationship, right? This result of these two segments, right, being equal to each other only happened because M is the midpoint of this chord, okay? All right, so now we need to now look beyond this information and go into our theory, right? So now this should now ring a bell to you that you have a theorem that says that if you have a line drawn from the center of the circle, right, to the midpoint of a chord, right, so this point there is the midpoint of the chord, right, then what happens, right, so that's the if, okay, then what happens is that that line, okay, will be perpendicular to the chord, right? So if that's the case, right, then we can apply our theory again and say, all right, so then that means that we are going to have OM, right, which is the line drawn from the center of the circle to the midpoint of this chord, being perpendicular, right, to the chord AC, right? So obviously then this 90-degree angle will then show up everywhere, okay? All right. So we've now read the given information. The last thing they say is let angle BDC equal x. Right, so BDC equals to x, and they've indicated that for us on the diagram as well. Okay, so that angle over there. Okay, cool. So now we've basically analyzed our diagram, we've pulled out information that was given to us, and we've also pulled out information that we can sort of like put onto the diagram based on what was given to us, right? So based on application of theory. Okay, right, so now once you've done that, okay, you're now ready to answer the questions. Okay, so we'll go question 9.1.1, right? It says determine, and the important thing here is with reasons, okay? And also we have in terms of the variable x, okay? Okay, so for A, they want us to determine with reasons the angle O1. Okay, so angle O1. Alright, so there is angle O1 over here. Let me just use a different color. Right, there's angle O1 over there. Right, it's an angle at the center. Okay, so if we trace backwards, right, and we see what is subtending O1, right, we see that it's subtended by this arc BC. Okay, so now we can draw from the theorem that says that the angle at the center, right, is always twice the angle at the circumference, right? So traveling from the same arc BC, right, we can still also go to the circumference, right, and we see that that arc is also subtending the angle BDC right at the circumference. Okay, all right. Okay, so then that's going to mean that angle O1 is equals to 2x. Right, so what's the reason? It's the angle at the center is equals to 2 times the angle at the circumference. Okay, so now once you've actually figured out something, another thing that is a good practice to do is then use a different color and put it onto the diagram. Right? So now we know that angle O1 is 2x. Okay. All right, so next 9.1.1b, okay, we need to determine with reasons, right, in terms of x, the angle ABO. Okay, so ABO, let's try to find that. ABO is basically angle B1 plus angle B2. Okay, all right. So now angle ABO, right, if you can see, it's actually part of this small little triangle over here, right? If I just highlight it in yellow, right, this small little triangle over here. Okay, and what we're looking for is these two angles over here. Okay, So they said in terms of x, which means that it's going to be related to this x that was given to us in the beginning in some way, right? And it is, right? Hopefully you can see that again, if you go to this arc, right, BC, right, you can look at the arc or you can look at the chord. It's up to you, right? You can see that basically what you have over here is angles in the same segment, right? If you look at angle B DC, right, which is the original x, okay, and its relationship with angle CAB, okay. You see over there, you've got angles in the same segment, okay. So which means that this angle A, right, angle A1, that is equals to x, okay. Right, so that's good because now that has brought us into this triangle, right, that contains this angle ABO, right, which we're trying to calculate, okay. And you can see immediately, right, that this is going to be 90 degrees minus x, okay, based on all of these relationships that we already have in place in our diagram, okay. All right, so now obviously we are going to have to, if you look over here, we have 4 marks. So we're going to have to start off with the fact of writing out why did we have this 90-degree angle over here to start off with, okay. So that's going to come from the given information, right? So we're going to say that angle AMB, right, so that angle over there, AMB is equals to 90 degrees, right? And the reason for this is because we have a line, right? And I'm just going to name the line. You can say, let's say OM, right? So the line OM, right? So line drawn, no, it's not drawn, it's line from center to midpoint of chord, to midpoint of chord AC, okay, right? So then now that we've established or given the reason why we have that 90-degree angle there, we can now talk about why do we have that angle A1 equal to x, right? And we already said that is angles in the same segment, right? So we're going to say angle A1 is equals to angle BDC, which is equals to x, and this is angles in the same segment. Right, I like to add over here subtended by arc, right? And I'm going to talk about an arc because I don't actually have the chord drawn into here, right? So if this was connected like that, okay, I would talk about the chord, right? But there's no actual line that was drawn there, right? No chord that was drawn there, so I'm going to talk about the arc, okay? So subtended by the arc BC. Okay, so then from there you can say therefore in triangle AMB, right, so triangle AMB, okay, angle ABO is equals to 180 degrees minus angle AMB, right, and minus angle A1, right. This is obviously sum of angles of a triangle, okay. Right, so then angle ABO is going to equal 180 degrees minus 90 degrees minus x, okay, which is going to equal 90 degrees minus x. Okay. Right, so now moving on to question 9.1.2, right, it says, prove that AB is a tangent to the circle that passes through the points A, AD, and R. Okay, right, so there's A over there, there's D, and there's R. Okay, so there's D, R, and there's A. Okay, right, so if AB, right, is going to have to be a tangent, right, to a circle passing through these three given points, right, then it's because of two different conditions, right? It's either that line, right, because currently it's a line, right? It's either AB, right, is perpendicular to the radius, right, of the circle, okay? Or you have the converse of the tan chord theorem, okay? So over here, right, if we look at this line AB, right, we can clearly see trying to prove that it is going to be perpendicular to a radius, right, is going to be tricky. Okay, so most probably what we have to do here is to prove the converse, right, of the tan chord theorem, right. So if we look over here, right, and we look at what this would actually subtend, right, notice that they said that the circle is passing through the points D, R, and A. Okay, so those 3 points on that triangle, right? So which means that the chord, right, would be this chord A, R. Okay, so then we want to see or to prove that this angle between the tangent and the chord, right, which is angle A1, right, that must then equal the angle in the alternate segment, which is going to have to be this angle D1. Okay, so what we are trying to prove here is that angle D1 is equals to x. Okay, if we can do that successfully, then we prove that the line, right, AB is a tangent. Okay, all right, so let's do that. Okay, so where to begin? Well, what I'm seeing now is this overall right angle triangle. Okay, so in that right angle triangle, right, the first thing I'm seeing is that angle DA2, right, is an angle in a semicircle, right, that's subtended by this diameter. Okay, and then we also have that in this right angle triangle here, right, so this one over here, a lot of colors happening now, right, this one in purple. Okay, this angle is going to have to be 90 degrees minus 2x. Okay, right, and then if you look at the overall triangle, right, we can then look at the sum of the angles of the triangle DAC, right, to calculate this angle D1. Okay, right, so then if we do our substitutions, right, to calculate what is angle D1, okay, for angle D2, right, that is angle D2, it's that x, right, plus angle A2, which is 90 degrees, plus angle C, which is 90 degrees minus 2x. Okay, all of this must equal 180 degrees. Okay, so we have that angle D1, right? We've got an x, we've got a minus 2x, so we've got minus x, right? We've got plus 180 degrees is equals to 180 degrees. So then you can obviously then see angle D1 is going to equal 180 degrees minus 180 degrees plus x, right, making angle D1 to also equal x. Okay, so now because of that, we can say, okay, that this line, right, AB is actually a tangent, right, because now what we've actually done is that we've successfully proved the converse, right, of the tan chord theorem, right. So then we're going to say, therefore, AB is a tangent. Okay, I would actually write it as they gave it, to the circle passing through the points A, D, and R. Okay, the reason is the converse tan chord theorem. Okay, right, so now for question 9.1.3, okay, I've brought in a very, like, basically a clean version of our diagram, okay, because this one is basically now very cluttered, okay. Right, so for this one, they say prove that AD squared is equals to 4DO squared minus 4AB squared plus 4MB squared. Okay, right, so chill, relax, don't run away. It's okay, don't worry. Okay, so with this one, you basically have to take this step by step, right? The tip that I can give you, right, is that when you see squares, right, it's either you're going to be working with two triangles, right, where that side is contained in both of them, right? So for example, the side AD, right, you're going to be looking at two different triangles where you have that side contained in both the triangles, or you're just going to be looking at the theorem of Pythagoras. Okay, remember the theorem of Pythagoras, we also have those sides squared. Okay, all right, so if we look at our situation over here, okay, if we wanted to identify two triangles that contain the side AD, right, then we would be looking at this main 90-degree triangle, right, ADC, and we could also work with the triangle ADB, right, this one. Okay, you can see you have that common side AD over there, right? But with this method, it is going to be quite tricky because with the second triangle, right, the orange one, okay, this is going to require us to use the cosine rule in some way, and I don't think we are actually going to go that far, right? Because if you can look at what we're trying to prove, I don't see cos showing up anywhere over here, okay? So we're going to have to abandon that plan. Alright, so if we abandon that plan, it means that we are going to have to actually concentrate on this right angle triangle, okay? And which means that if we're concentrating on this right angle triangle, we're basically applying Pythagoras theorem, okay? So let's do that, okay? So we're going to say in triangle DAC, right, Pythagoras theorem says, right, if we want to now focus on the side AD squared, because that's not the hypotenuse, Pythagoras will then say that that side is equals to the hypotenuse squared minus the other side, so AC squared. Right, so this is Pythagoras. Okay, all right, so now compare. DC, is there DC anywhere here? No, but we have this DO, and if you can look at DC, right, DC actually contains DO, right, and in fact DC is a diameter, right, so DO is the radius, right, so DO is basically, sorry, no, the other way around, DC is basically twice DO, okay, so we can do that substitution. Okay, so we're going to say over here that twice DO is DC. Don't forget that was originally squared. Okay, then we have minus, right, AC squared. Is there an AC over here? Nope. There's an AB. An AB shows up over here. You can just highlight it. Okay, this is where AB shows up. And there is a MB. Right, so there's MB. Okay, so if you can think back to this original diagram that we had, we already identified this triangle to be a right angle triangle as well. Okay, so what's stopping us from using Pythagoras theorem in that right angle triangle as well? Well, nothing. Okay, so we'll leave this AC squared as it is. Okay, and now what we're going to do, right, I'll carry on here. We're going to apply the theorem of Pythagoras to the small little triangle. Right, so we're going to say in triangle AMB. Okay, what are we looking for? We're looking for AC. Okay, so where's AC? Alright, again, AC is this full length, right? But we also had that this is the midpoint, right? So then AM was equals to MC, right? So yet again, we can do this whole thing of saying that AC, okay? I can just remove all of this. I'll just put this back. Right. So AC is twice, okay, it's twice, let's use AM, okay, because that is in this triangle that we are now concentrating in, okay, so AM, and that still needs to be squared. Okay, so basically in this, let me just highlight it, in this orange triangle, it's orange, previously it was yellow, sorry. Okay, I'm going to be focused in on looking for an equation for the side AM, right, so that I can substitute it into this small little equation that we are developing over here, right? So then we're going to have that AM squared, right? That's going to be equals to the hypotenuse squared, so AB squared, minus the other side squared, so MB squared. Okay, this should make you happy because now you're seeing MB there, you're seeing MB there, you're seeing AB there, AB there, and there's a DO and DO. And what we're going to do is we're going to now substitute AM squared right into there. Okay, right. So if we do that, we're going to have, simplifying over here, we're going to have 4DO squared, right? Then we're going to have minus, okay, and let's just simplify this first. So it's going to be 4am squared, right? And we know what am squared is. It's this, okay? Okay, so we can do that substitution. We're going to have 4do squared minus, we still have that 4 on the outside. We're substituting am squared, which is ab squared minus mb squared. Okay, so simplifying again, we're now going to have minus 4am, sorry guys, 4ab squared, right, and then we're going to have plus 4mb squared, right, and all of this is equals to ad squared. Okay, so now let's compare, right, we've got 4do squared minus 4ab squared plus 4mb squared. Okay, so that's exactly what they wanted us to show or prove. Yeah. Alright then, so then that's it for today's video. I hope you guys learned something and I will see you next time.